The chronic sugar translates via conveyor belts into the rotating stainless steel drums for a thorough wash.
Every day, the global food industry produces billions of eggs. From breakfast tables to large-scale food manufacturing, eggs are one of the most widely consumed proteins on Earth. But behind this enormous supply lies an overlooked byproduct. For every egg processed, a fragile shell remains usually treated as waste. Across industrial bakeries, food factories, and egg processing plants, mountains of eggshells accumulate daily. In large processing plants, eggs are cracked, separated, and transformed into liquid egg products used in bakeries, sauces, and packaged foods. The process is highly automated, designed to handle millions of eggs per day, yet the shells, which make up nearly 10% of the egg's weight, are often discarded in bulk. Traditionally, these shells end up in landfills, animal feed, or low-value fertilizer. But what appears to be fragile food waste actually contains a remarkable material, one that scientists have begun to recognize as incredibly valuable. An eggshell may seem delicate, but its structure is surprisingly sophisticated. Nearly 95% of the shell is composed of calcium carbonate, a mineral that forms an intricate crystalline lattice. This architecture gives the shell both strength and lightweight protection for the developing embryo. For biomedical engineers, this chemical composition is incredibly important. Calcium is the primary mineral found in human bones. When properly processed, the calcium compounds inside eggshells can be transformed into biocompatible materials capable of supporting bone regeneration. Bone graft materials are used in surgeries to repair fractures, rebuild damaged bone, and assist in dental implants. These materials must mimic the natural mineral structure of human bone, allowing new tissue to grow and integrate safely within the body. What if a waste product from the food industry could be transformed into a life-saving medical material? Inside specialized facilities like this one, engineers are doing exactly that, turning discarded eggshells into high-purity biocalcium used for bone graft substitutes. But before eggshells can become medical-grade biomaterials, they must undergo a precise transformation. The journey begins with careful collection, sorting, and purification, removing organic contaminants and preparing the shells for chemical refinement. Before eggshells can be transformed into medical-grade materials, they must first be captured within the industrial food supply chain. Modern egg processing plants are designed to collect shell waste directly from cracking machines. This step prevents contamination and allows the shells to be recovered in large quantities, sometimes several tons per day. Once collected, the shells are sealed in specialized containers and transported to processing facilities. Logistics are carefully controlled to prevent microbial growth and decomposition. Because the final product will be used in medical applications, strict material traceability is required from the very beginning of the supply chain. At the factory, the eggshell waste enters the controlled processing environment. Each batch is scanned, logged, and inspected. Even though eggshells are a natural material, their biological origin means they can carry proteins, membranes, and microorganisms that must be removed before further refinement. The first major step is intensive washing. High-pressure water jets and rotating drums remove dirt, residual egg white, and other organic material. This cleaning process is essential because proteins left behind could interfere with later chemical treatments and compromise the purity required for biomedical materials. Inside every eggshell is a thin organic membrane. While useful in nature, this layer must be removed for biomedical applications. Specialized separation machines use mechanical brushing and controlled airflow to strip away these membranes, leaving behind mostly pure mineral shell fragments. Next comes sterilization. The shells are exposed to carefully controlled heat to eliminate bacteria and deactivate any remaining organic material. This stage ensures the material meets strict biomedical safety standards before it moves to the next phase of processing. After washing and sterilization, the shells must be thoroughly dried. Removing moisture prevents microbial growth and prepares the material for grinding. At this stage, the shells are now clean, sterile, and composed primarily of calcium carbonate. The final step in pre-treatment is size reduction. Heavy-duty mills crush the brittle shells into a fine mineral powder. Increasing the surface area of the material makes it far easier to control during the chemical transformations that will soon convert this simple powder into advanced biomedical calcium compounds. After cleaning and grinding, the eggshells are now reduced to a fine calcium-rich powder. Chemically, this powder is composed mostly of calcium carbonate, a mineral that forms the foundation of the entire transformation process. But before it can become a biomedical material, its chemical structure must first be altered. Precision is critical at this stage. Automated feeders measure exact quantities of calcium carbonate powder and deliver them into high-temperature processing units. Even slight variations in material ratios could affect the purity and crystal structure of the final biomedical compound. The powder now enters a process known as calcination. Inside this furnace, temperatures climb to nearly 900 degrees Celsius. At this extreme heat, calcium carbonate breaks down, chemically releasing carbon dioxide gas and transforming into calcium oxide, a far more reactive compound. At the molecular level, this reaction is dramatic. The intense heat drives carbon dioxide out of the crystal lattice, leaving behind calcium oxide. This material is highly reactive and serves as the critical building block for producing hydroxyapatite, the mineral that makes up the majority of human bone. In the next stage, calcium oxide is introduced into a carefully controlled chemical reactor. Here, it reacts with phosphate compounds under precise temperature and pH conditions. This reaction gradually forms hydroxyapatite crystals, the same mineral naturally present in bones and teeth. Hydroxyapatite crystals begin forming as calcium and phosphate ions bond together in solution. Engineers carefully control the reaction environment to mimic the natural mineralization process found in human bone formation. Once the reaction is complete, the newly formed hydroxyapatite particles are separated from the liquid mixture using industrial filtration systems. What remains is a highly pure biomaterial powder ready for the next stage of refinement. What began as discarded eggshell waste has now been chemically transformed into hydroxyapatite, a biomaterial nearly identical to the mineral structure of natural bone. But before it can be used in medicine, this powder must still undergo precision engineering to create the porous structures required for bone graft substitutes. Hydroxyapatite powder alone cannot repair bone. For the material to function inside the human body, it must be engineered into a precise structure known as a scaffold. These scaffolds act as temporary frameworks that allow new bone cells to attach, grow, and eventually replace the implant material. To shape the powder into stable forms, engineers add specialized binding agents. These temporary materials help hold the hydroxyapatite particles together during processing. Later, they will be burned away, leaving behind a carefully designed network of microscopic pores. Some bone graft materials are produced as small granules. These particles can be packed into bone defects, where they act as mineral building blocks that gradually integrate with the surrounding bone tissue. For larger bone repairs, the material must be molded into three-dimensional scaffolds. Engineers design these shapes to match the mechanical needs of the body, ensuring the implant is strong enough to support tissue while remaining porous enough for biological growth. The key to successful bone regeneration lies in porosity. The scaffold must contain a network of interconnected microscopic channels. These pores allow blood vessels, nutrients, and bone-forming cells to move through the material, transforming the implant into living bone over time. Next comes sintering, a high-temperature process that permanently bonds the hydroxyapatite particles together. Inside specialized furnaces reaching temperatures above 1200 degrees Celsius, the material becomes strong enough to survive inside the human body. After sintering, the scaffolds cool slowly to prevent structural stress. The result is a rigid yet porous biomaterial structure that closely resembles the mineral framework of natural bone. At this stage, the eggshell-derived material has been transformed